And once in service, it's not just the engineering staff who are responsible for maintaining that structural integrity. Both the ground and air crews have an equal responsibility. For aircraft are subject to aerodynamic and inertia loads. This means we have to consider not only the static strength of the structure, but also its fatigue life. And this can be severely affected by what at first seem quite minor actions. But before we look in more detail at fatigue and its causes, let us first consider static strength. For military aircraft, the performance required is specified by the air staff in terms of speed, payload, range, maneuverability, etc. In meeting these objectives, the design team defines the design limit load. This is the greatest load that should occur in the operating conditions specified. Eventually, these limits are published in the CA release document. In normal circumstances, this load should never be exceeded. To provide sufficient safety factors, in the event of an emergency, however, the structure can operate safely without any long-term after-effects up to the design proof load. This is normally 1.125 times the limit load. Beyond this point, the structure will still function, up to the ultimate load, but in doing so, large deflections and permanent damage will probably be caused, resulting in control malfunction. The ultimate load is generally a mere 1.5 times the limit load. Once the ultimate load is exceeded, the structure fails. The static strength of materials is quite easily measured, and the characteristics of the metals regularly used in aircraft construction are well known. There is now an increasing use of composite materials such as carbon fiber reinforced plastics. These provide great strength and stiffness while allowing a reduction in weight. This strength may be very directional, however, and may be directly affected by conditions of heat, moisture, and ultraviolet light, which don't affect metals to the same degree. But in general, operational aircraft only rarely present problems due to insufficient static strength under the applied loads. The never exceed limits are clearly stated, and the dangers of passing them are obvious. But for fatigue damage, it's a different story. During recent years, several RAF aircraft have been lost due to fatigue. For many others, fatigue damage has fortunately been identified at an early stage. But correcting the faults means long and costly repair work. Wing modifications and reconditioning for the Hercules fleet, for example, cost £80 million. These extremely high costs, the reduced availability of operational aircraft, and the threat to flight safety make fatigue a matter of great concern to the RAF. To see why the air crew and ground staff can aggravate this problem, we need to learn a little more about fatigue. Each time a piece of metal is subjected to a variation in load, fatigue damage occurs. The amount of fatigue damage depends on how great a change occurs in the level of tensile stress, the stress being the load per unit area of cross-section. As we said earlier, the ultimate strength is easily measured. But suppose we take a much smaller repeated stress. There is no permanent deformation. But if the loading cycle is applied many thousands of times, failure will eventually occur due to fatigue. The lower the stress, the more often it must be applied, but failure will occur in the end. From the results of tests like these, we can plot a curve known as the SN curve. It indicates the number of cycles necessary for failure at different stress levels. If several identical samples were tested, however, failure wouldn't always occur at the same number of applications. There would be considerable scatter. The curve is really a mean through a series of points. Now, if we only used plain sheets of metal, fatigue would cause few problems. Even high stresses need to be applied many times to produce failure. But put a hole in it, and the picture changes dramatically. Far fewer stress applications will cause failure. Bolted joints or lugs create similar problems. The fatigue life becomes much shorter. Let us see why this is so. The answer can be seen when a model is viewed using polarized light. Areas of stress concentration build up round the hole. The colored bands are closer where the stress is higher. And it's not only holes which add to the fatigue problem. If any cracks are present, the stress builds up round the tip so that it may be many times that being applied to the metal as a whole. So the crack grows quite easily. Such cracks can grow from tiny flaws in the metal as the sample is fatigued. Here we are seeing the process speeded up many times. At a certain point, a critical crack length is reached. Here we can see the crack quite clearly as it nears this point. The component is now so weak that if a stress is applied equivalent to the maximum G allowed in the aircrew manual, failure could occur. As we have seen, such failures do not occur only in the laboratory. For all aircraft, there are many stress cycles which contribute to fatigue. Air turbulence produces frequent, fluctuating loads. Buffet, which causes high-frequency loading, is particularly damaging. Pulling high G puts the whole frame under stress, so tight maneuvering can cause a lot of fatigue damage. Air-to-air refueling operations can also affect certain components. Nimrod fins, for example, suffered from fatigue problems due to poor lateral stability and the effects of flying in the tanker's wake. And in formation flying, the rear aircraft is always more severely affected than the others. For low-level operations, gusts are more prevalent, and their effect on the aircraft is more acute. Changes in pressurization contribute. And the transition from ground to air and back is also important, especially for transport or tanker aircraft, such as the TriStar. As can be seen, the wing loading for aircraft with the undercarriage on the body changes drastically on touchdown. The all-up weight and even the distribution of fuel and stores can have a critical effect on fatigue consumption. Center line weight, such as freight or fuel in fuselage tanks, increases the stress towards the wing roots, whereas distributing mass outboard can have a beneficial effect. Taxiing and towing also play a part. Even on a good taxiway, there will be some bouncing. Rough surfaces can cause very high stresses at the wing roots. The ground running of engines can have a significant effect on the airframe, and less obviously on the undercarriage. The engine itself suffers from fatigue. High cycle fatigue may affect blades or discs owing to internal dynamic effects. And there is the additional low cycle effect due to rotational stresses in response to changing engine settings. Helicopters have major structural components which experience a relatively high number of load cycles. Even though the stress variation may be small, thousands of cycles will cause fatigue to accumulate quite rapidly. Particularly damaging operations include carrying large and heavy underslung loads, transition to hover, and flying sideways. Both helicopter and engine components have to be designed to operate under high cycle fatigue, at the right-hand end of the SN curve. Stress levels may be quite low, but repeated this frequently, they can cause damage.
Of course, designers are aware of all these factors and try to minimize the problems. Modern combat aircraft are generally built in accordance with a safe life design philosophy. This means that during the planned life of the aircraft, the designer intends that no crack should occur. To determine the safe life for the aircraft, use is made of test data from many years of research, as well as from past experience gained by monitoring the fatigue consumption patterns of previous RAF aircraft. These figures are usually confirmed using a full-scale fatigue test on one of the production batch of the new aircraft. Based on all this testing and data, the designer calculates a value for what is known as the mean life of the aircraft. By applying certain safety factors to allow for any scatter in the results, we obtain a safe life, known as the fatigue life. For modern combat aircraft, a planned fatigue life of 5,000 to 6,000 hours is fairly typical. The damage expected during this life is now made equal to a number of fatigue index units, FIs, ideally 100. This is done because the number of load applications can't be related to flying hours. So, if the aircraft is to have a life of 20 years, it can use up an average of 5 FI each year. If it uses more, the aircraft won't last for its intended life. And there's one more crucial aspect to consider. The testing and calculations assume that the aircraft is going to be used in a particular way. The load cycles being applied to the fatigue test specimen under computer control are based on the sortie patterns and flying role defined by the air staff. They're defined in the Statement of Operating Intent, the SOI. But the information gathered together in the SOI doesn't necessarily remain unchanged. Aircraft usually suffer from growth in basic weight, and new roles and weapons are developed. So the SOI must be regularly updated. And effective data collection is also a prime requirement.
At present, in-flight fatigue monitoring on most fixed-wing aircraft depends on the fatigue meter. This instrument measures the vertical accelerations at the aircraft's center of gravity during flight. Each time a set G level is exceeded, the event is registered by a counter. By taking the readings from these counters and using them in a specific-to-type formula, we can estimate the fatigue damage incurred by each flight. Collecting this information allows us to check how fast each aircraft is using up its fatigue life. To avoid premature grounding of aircraft, or even catastrophic failure, the recording of this information, by the correct completion of Form 725, is vital. Aircrew and ground staff must make the effort to see that it is done properly. The forms need to show the fatigue meter readings clearly. so that the differences can be calculated easily. Sortie profile codings are especially important. Processing of the data is usually done at the Maintenance Analysis and Computing Establishment, known as MACE, at RAF Swanton Morley. The computer allows us to publish a precise record of an aircraft's fatigue consumption all through its life. However, where flights have not been metered or coded, or where the forms are illegible, both the defective flight and the next sortie cannot be processed properly. We have to assume the worst, and so may waste valuable fatigue life. On some aircraft, it is possible that a whole year of their life could be wasted for reasons of this sort. The records produced by MACE enable us to identify which aircraft are using fatigue life faster than average. A role change to less severe duties may be possible, or temporary flying restrictions may be needed. Such records also help in planning fleet modification programs due at a particular level of fatigue consumption. Another major use for fatigue meter readings is to feed back information to designers about the damage caused by the different sortie profiles. For management reasons too, it is important to know how much fatigue is accumulated by various kinds of flying. But although the fatigue meter is very useful, it does have limitations. In flight, it only counts accelerations acting vertically through the center of gravity. It doesn't tell us what's happening to the tail, the fins, and so on. Nor does it take account of aircraft configuration, Mach number, or weight distribution. It doesn't register transitions between air and ground, and it doesn't work on the ground, so damage incurred while taxiing and towing goes unmonitored. Furthermore, if aircraft are used in ways not correctly accounted for, fatigue problems may start sooner than expected. These Harriers, when carrying out a particular type of sortie, operated without SNEB pods most of the time, whereas the fatigue meter formula assumed they were fitted, providing what is called bending moment relief. The result? Fatigue was consumed much faster than anticipated. Fleet management, in the form of strict quotas of fatigue consumption on each aircraft, was necessary. This type of occurrence also highlights the need for the statement of operating intent to be kept under constant review. In order to overcome some of the limitations of the fatigue meter, to assess the effects of changes in usage, and to validate fatigue calculations, some aircraft are now being fitted with an OLM system. This stands for Operational Loads Measurement, and comprises a system which measures the strains at various key points in the structure and records most of the flight parameters. Such systems have already been installed, for example, on the Buccaneer and the Tornado. They are being fitted to several other types of fixed-wing aircraft and to some helicopters. Here, OLM will relate the fatigue consumption of the main rotor shaft and other critical components to various flight conditions. It may then be possible to devise a continuous monitoring system for such areas. This is needed because such areas are often very sensitive to changes in usage or configuration, sometimes resulting in premature cracking. Cracks can also occur unexpectedly because of corrosion or accidental damage. The fatigue test specimen helps us to identify the areas most at risk, but occasionally the first evidence of damage is the discovery of actual cracks on in-service aircraft. In these cases, we can only assure structural integrity by reliance on inspection.
You recall that we defined the philosophy governing military aircraft design as safe life. An alternative philosophy used is fail-safe design. In this case, structural integrity is assured by detecting damage before it weakens the structure dangerously. Virtually all civil-type aircraft and their military derivatives, such as VC-10, TriStar, BAE 146, are so designed. The main point of fail-safe designs is that they're tolerant of quite large defects, several inches long perhaps, which grow only slowly. By contrast, critical crack lengths for safe life structures may be quite small, only tenths of an inch. And once started, a crack may grow to this size quite rapidly. Whatever the design philosophy originally used, examination for cracks is a vital part of maintaining airworthiness. The correct frequency of inspections must be observed.
As we said earlier, cracks could be started by careless handling on the ground. A small scratch or hasty withdrawal of a drill could cause stress raisers from which cracks will start growing. Corrosion, too, is very harmful in starting and accelerating the growth of cracks. It should be treated immediately it's spotted. For composite materials, neither corrosion nor fatigue should be a problem, but they do present other snags. Small impacts, dropping a spanner like this, for example, can cause delamination. In this case, it's just visible. On other occasions, the damage may be internal, with no trace of it on the surface. Repair must be carried out to the highest standards, and special techniques and equipment may be required. Since small cracks in highly stressed structures can be so dangerous, the need for very sensitive methods of finding them becomes vital. Several methods are now in use for the non-destructive testing of RAF aircraft to check for cracks. These include radiography, ultrasonics, eddy currents, and dye penetrance. Visual inspection is still important, even though it cannot pick up very small cracks. Each technique has its own limitations, and allows it to experience of the operator. To exploit these methods, we really know where to look and what to expect. This is particularly so for new materials. It's clear that finding fatigue damage or other structural defects before they affect flight safety is a key step in preventing accidents. But to keep the problems at bay requires the active cooperation of all who fly and maintain RAF aircraft. Firstly, remember that aircraft are designed with limited strength. The safety factor before structural failure occurs is only 1.5, and the never exceed limit, which normally corresponds to the DLL, means precisely what it says: never exceed. And fatigue life is a valuable commodity. Help to conserve it with responsible flying. Don't pull more G than you need. Don't forget the effect of fuel and freight loading. Try to avoid unnecessary circuit or low-level work, or excessive throttle movements. Any heavy landings must be reported, as they could affect the strength of the undercarriage and other parts of the structure. Avoid fast taxiing and towing. Remember that helicopter components are working at the high cycle end of the SN curve. Try to minimize damaging activities. Use the correct tools at all times and prevent damage or corrosion, which could start cracks growing. Keep your eyes open and report any cracks you do find. Become familiar with the new procedures that follow from the introduction of composite materials. Report any damage, no matter how trivial it may appear. Ensure that fatigue meters are serviceable and complete the forms clearly and accurately in full. Make sure that the statement of operating intent reflects the pattern of use. Inform the air staff of any deviations. Only if we all realize the limitations of aircraft structures and the implications of fatigue can we hope to contain the costs involved, to increase aircraft availability and to maintain flight safety.